Okay, yeah, I'm going to talk today, as Christoph's mentioned, about using NGS data to look at drug resistance. These are tools that we're actively using in PANGEA, developed initially for the HIV sequencing protocol, was developed initially for the Popart phylogenetic clinical trial. I should say that's on the back of work that we did looking first at hepatitis C. And the methods are widely transferable to other viruses, and that's all I'll say about that. But the method has been highly optimized to look at the specific problems, the specific challenges that we have with the kind of molecular epidemiology work that we're doing. And so I will talk a little bit about Popart. Mostly the data that I'll show is about resistance in Popart. It's all work in progress. The sequencing is just about complete for this clinical trial. Popart, as you are aware, is the largest clinical trial of treatment as prevention ever conducted, and the phylogenetic sub-study involves the communities in Zambia and individuals who consent to the phylogenetic sub-study give a sample at the beginning of the trial. We sequence the virus within the host, and we use that information to primarily map out these networks of transmission. And we have developed the methods, the sequencing and the analytics specifically to identify, to characterize these networks with directional information that allows us to identify the transmitters and therefore the correlates of transmission. And that allows us to ask questions about what were the factors that associated with those transmission events that occurred during the Popart clinical trial in spite of the intervention. We have a few ideas in terms of what the things that we'll be looking at, including the role of acute infection, the role that migration has played, and along the way we'd like to look at drug resistance. And the Popart trial has been unblinded at CROI this year. At the steering committee last week, Richard Hayes gave a description of the primary outcome and what it meant. And I think one of the clear messages is that we did observe a difference, a modest difference between arms A and C in the clinical trial in terms of the incidence observed over time. But there were some as yet unexplained outcomes, particularly in the differences between the two intervention arms, A and B. But I think, and this is now fourth or fifth clinical trial of treatment as prevention, and of course they've all shown quite modest effects, or in some cases no effect at all on the level of incidence. And the questions that lay in front of us now are really what are the reasons for that? How is it that you can have a situation where treatment is on the individual basis almost 100% effective at preventing transmission, yet these community-based programs to roll out drugs seem to give quite modest results. And I think one of the questions, and we'll ask the question right now, whether or not drug resistance could be playing. It seems reasonable to hypothesize that if treatment isn't effective in the individuals you're giving it to, then of course they could pass on their virus, and so there's a host of questions that we'll be asking in the course of the Popart phylogenetic trial. The main ones I've listed here. We should start by looking at what the prevalence of drug resistance is within Popart at baseline before people were enrolled, at the point that people were enrolled, and ask to what extent drug resistance limited the effectiveness of treatment prevention of new infections within the trial. And we have, of course, not only the sequencing, but the tools in the modelling arm of the trial to simulate what would have happened, for instance, if there was no drug resistance in that kind of counterfactual scenario. And more kind of and then linking that to the communities, is it possible that drug resistance contributed to the heterogeneity that was observed in the trial's outcome? And other questions that we won't be asking directly, but other groups also in Popart will look at the other side of that equation, which is, how did Popart impact the levels of drug resistance in the communities that were enrolled. And of course, HIV is an evolving problem, and these are figures from Ravi's paper last year. This was a meta-analysis that confirmed the suspicions that drug resistance is an increasing problem, particularly in Africa. The plots on the top show the prevalence of non-nucleoside reverse transcriptase inhibitor resistance that I refer to as NNRTI resistance throughout this talk. And we see that the prevalence seems to have increased, and which is totally, in South Africa, and then lower levels of increase in the other class of drugs that are widely prescribed in Africa, the nucleoside reverse transcriptase inhibitors. I don't think it's the case that we should be too reassured that the NRTI resistance isn't going to become an increasing problem.
Children.
Has somebody got their microphone on? Can they just mute it?
They are not surviving as well. They have.
Can you just check that you've got? Can everyone just check that they've got their microphone?
Sequoia, is that Sequoia Can you please turn your microphone on?
All of you familiar with the DStat? It remains a global health burden.
Okay. All right. So one of the early observations that one of the early observations from the preliminary analyses of the data as it was coming in last year. This is data that was presented at IAS last year on the first 1,000 sequences, which was a comparison just between the drug resistance that we observed in Zambia in Popart with the drug resistance that we observed in Beehive, a European cohort of mostly clade B viruses, and it's striking that how different the patterns of resistance are. Unsurprisingly so, because different drugs are prescribed in different parts of the world. And you can see that the drugs are listed on the bottom. I'll just go back one. The consensus sequences make up the tree here, and for each consensus sequence, we summarize the resistance that we derive. I'll explain more about how we derive resistance in a few slides. And the drugs are divided into the different classes. And where in Europe, where we prescribe more protease inhibitors, we see more protease inhibitor resistance. In Africa, where the majority of nearly all the drugs are either a combination of NNRTIs and NRTIs, you see much higher levels of NNRTI resistance overall. That may be partly a genetic predisposition to some of the mutations that are more commonly seen in that part of the world. But what's interesting is that you see the NRTI resistance almost always in association with high levels of NNRTI resistance. So, it seems clear that, you get the NNRTI resistance first and the NRTI resistance will follow. So, I don't think we should be, as I say, I don't think we should be too reassured that the levels of NRTI resistance won't increase. It's just that there's likely to be a lag. And of course, this is relevant moving forward into an era of integrase-based therapies where NRTIs will still be part of that therapy regime. I think beyond the Popart analyses that we're doing, we'll begin to hopefully we'll be able to refine this kind of drug resistance forecast to make stronger predictions for the future, and specifically in the areas that we've been working in through Popart. And I think to do that, it'll be good to dissociate the effects of transmitted drug resistance versus de novo acquisition of new mutations within individuals. And to do that, we're going to have to get to grips with the rates of transmission of drug-resistant virus and rates of reversion of mutations, and also the rates of selection of new drug-resistant mutations. We need to better understand the role that low-frequency drug mutations are having, the importance of mutational load, and the role of multi-drug combinations of drug resistance, that should say. So different mutations all linked together within the same virus. And I think that it's important to kind of keep this in context of treatment as a means of preventing new infections, and what does that mean for the future of this strategy for preventing incidents on a community level. And we're also interested in the translation and thinking about what the clinical role for drug resistance is going to be. Do we need it at all? Can we predict drug resistance without a test? And how do we use the information? Is the answer better empiric choices of therapy? Do we put everybody onto dolutegravir and just hope for the best, or do we aim for a more targeted approach or a heightened surveillance? I mean, first of all, it's worth just asking the question if it's reasonable that any viral factor at all, any property of the virus, could have an effect on a trial like Popart. The hot topics of conversation are on the role of migration. It's true that the majority, nearly all the virus that we see in Zambia, here's a tree of the phylogenetic tree of the consensus sequences of all the samples that we've obtained from the healthcare facilities. These are people turning up to the healthcare facilities at the beginning of the trial. Represents about 80% of the total data that we will have within Popart phylogenetics. And they're all clade C. And if people are moving around that much, then is it reasonable to say that to suspect that these incidents, that the differences in incidence we see could be a property of the virus? Well, we looked at this by looking at we asked the question how structured is the virus according to the communities that the virus was sampled in. What we're looking at here is an ancestral state reconstruction of the sequence information of the consensus sequences we've obtained within the phylogenetic trial. It's the same tree that I showed you on the previous slide, and we've used a maximum likelihood to estimate what the likely states, the likely communities, sources of the nodes within the tree are. And that's given that we know what the actual communities from where each one of these sequences was obtained. Now you might look at that tree and you might think, well, there's no, this is just a mush of the communities, and it just confirms the suspicion that that this is just virus swarming around Zambia and not really structured by community at all. But actually, we can simulate that. And if I just randomly assign the communities now to tips on the tree, just completely jumble them up and rerun the analysis, it looks something like that. So, I mean, it's pretty clear that there is quite a lot of structure within these communities. And if we zoom out and we consider the communities in the south, with the central communities here and the northern communities, and we say, well, is there a difference there? You can see, well, there really is, and you can see that the communities in the south shown in green here, the communities in the north are shown in blue, and the central communities seem to be feeding into the north and the south. It wasn't my intention that this tree would accurately represent the kind of the compass, but it does seem that the southern communities have fallen at the bottom of the tree and the northern communities at the top. So there is structure there. So I think it's reasonable to consider the possibility that properties of the virus, like resistance, could be having an effect. We'll talk a little bit about the method. The method has been through an extensive amount of optimization. We're a team based in Oxford. Myself, Maria Teresa, one of the postdoc, also now working on PANGEA on the sequencing. We developed the protocol for sequencing HIV with input from Rory Bowden as part of the Oxford Viromics Consortium here in Oxford, and George McIntyre Cockett is our technician that implements this high throughput protocol for obtaining all this information. So we start with plasma. We extract the nucleic acid from the virus particles within plasma using the EasyMag bioMérieux system, boom-based extraction protocols with magnetic beads without using any carrier. And then we've tried various, many permutations of different combinations of extraction and library preparation, enrichment and PCR, and we've settled on a library preparation method that uses the SMARTer protocol, which stands for switching mechanism at the 5' end, and it is a way of generating your library within a single reaction without the need for enzymatic ligation steps. It's highly efficient. It does a good job of getting your adapter sequences and your index, which you need to index your libraries without cleanups and steps that can lose material along the way. We then apply an enrichment step where we use oligonucleotide probes designed to capture the full epidemic diversity of HIV. These are probes that are biotinylated, and we can fish them out. We can fish out the sequences that they bind to using magnetic beads. And then we sequence on an Illumina instrument. That's a MySeq that's shown there. We tend to do our preps now in 384 samples all at once. So we use a HiSeq platform, and we miniaturize the assay and reduces the cost to around £30 per sample. And one technician can get right the way through this protocol for around 400 samples every week. And so it's a very fast and efficient way of doing the job. But because this is one part of the pipeline, and it generates all of this information that we're using within Popart and PANGEA. So we discovered early on that the sequencing we do more than other next generation sequencing protocols is highly quantitative. So much so that if you include a standard curve of quantitative standards, so that's just 10-fold serially diluted virus and cultured virus within every run, then you can infer the viral load. Of course, you get the genotype. You've seen the trees that we're able to draw from the whole genome consensuses. We can draw the transmission networks. Matthew talked about that in detail last week. And we can get the resistance information as well. Now, an advantage, but of course, because it's quantitative, you get quantitative estimates of the drug resistance mutations that you see within host, and you can link all of that information to the viral load and the transmission networks, and that's all very good. So this is we think that this is an improvement on the previous method that we were using within PANGEA. Just a reminder of how this used to be done. So this was with again an RNA extraction and a cDNA synthesis and PCR within a single step, where the virus was amplified in four overlapping amplicons. I think it was the number of amplicons, or the 5 shown there, which I hadn't noticed before. This is less quantitative, and the reason that that's less quantitative is because there are two separate PCRs within that reaction. You have to PCR amplify your amplicons. So you PCR amplify to generate your amplicons, and then you fragment those amplicons, and then you PCR amplify them again. Now, when you do your deduplication, which is important because that is removing. That's a step that will remove the PCR duplicates. So you should be in our protocol, in the enrichment protocol, you're approximately left with one sequence per short template that you had in your input material. But that's not the case for the amplicon-based approach, because you can only deduplicate to this point here. You can't then deduplicate the information. The duplicates that arose from your initial PCR. I mentioned that we tried lots of methods to get to identify that SMARTer was the way forward, and so this is the switching mechanism at the 5' end of the RNA template. So you random prime your RNA to generate your first strand of cDNA, and then there's a fancy template switching process here that within the same reaction adds an adapter to this end of the molecule that allows you to generate your second strand going straight into the PCR. You can do similar things with enzymatic ligation, but we find that this process here is much less efficient, and we learned early on that we were getting higher yields of reads. It's just as quantitative, but overall you get high yields of reads from SMARTA than you do with the enzymatic ligation methods. That in turn means that with if you're able to rescue more of your template in the initial step, you can afford to do less PCR to generate your library. Now that's important because everything in molecular biology favours that's easy, and that tends to be the amplification of short fragments. So if you have to do lots of PCR, you'll very quickly start to bias your library in favour of the short fragments, which is a problem for the within host phylogenetic analyses that we needed to do. So that was it's a key finding and a key principle really that if the PCR in general is bad, you need to do as little of it as possible, and you need to do everything that you can with whatever method that you choose to make sure that every initial RNA template has just the same chance as everything else as getting sequenced. So the sequencing is part of a complex and increasingly complex bioinformatic and analytical pipeline that Chris and Matthew had developed actually before I'd even started with Marie-Theresa in the group, and now some of the later stages of the pipeline with Tanya Glubchik, we're able to kind of add on to this, but it's all one pipeline that generates clean data that can feed into the methods for quantifying viral load and assessing drug resistance. So translating this method and adopting this method, you either need to use the whole thing, we think, or you give serious thought to what each step is doing. So the newest addition to the pipeline is DRM-seq, which is a method for rapidly inferring drug resistance. So I'll talk a little bit about that now. So it's been designed specifically for the kind of data that we're dealing with the Oxford method, BE-seq. And the general principle is that we want to infer drug resistance at the read level. We want to be able to know how the drug resistance, what the patterns of drug resistance look like within host, to get a grip of how these variants are being transmitted and how they're evolving. And many of the other pipelines that are out there are inferring drug resistance at the consensus level only. Even with NGS data, there are pipelines out there that are looking at the frequency of nucleotides at each site and making inferences of what that means for the quantity of variants circulating within host. So we prefer to do this with a codon-aware alignment of the short read data. A lot of the pipelines that are out there are working with clade B as a reference for mapping, and we figured that most of the virus that we're working with is clade C, and trying to map a sequence to the wrong to a mismatched clade could cause all sorts of problems, particularly with inserts and deletions. So we've developed a protocol where you actually feed a panel of references from a variety of clades, and so the process is agnostic to the mapping is agnostic to whatever clade you start with. You don't have to know what the clade is of the virus that you're starting with. We've implemented this so that it uses the resistance algorithm, the database that constantly updates from HIVDB. That's the Stanford database, and then we're providing a quantitative summary of read data, filtering on read counts and percent prevalence threshold, whichever of those you want to choose. It generates a report, and it does so very quickly. So a high spec laptop can process 6,000 reads in just under 2 minutes, and we managed to process the whole of the Popart healthcare data. That is 34 million reads, all spanning the Pole region, in just over 10 hours. The other thing to say about it is that it's very flexible. It allows us, you can in theory use the pipeline to annotate and understand the evolution of other amino acid changes that are occurring within hosts, such as CTLSK, envelope glycosylation, and if you just need to feed it the information to start with. So there's a review, I should have cited it, entitled the Winnipeg Consensus on ways of looking at on the important parameters, the important things to consider when using drug resistance in inferring drug resistance from next generation sequence data. And I think we've just about answered all of the kind of primary targets. At the sequencing level, it's important that you consider the quality of bases, read length, and the possibility of contamination. And Shiver and Filoscanner handle that upstream of DRM-seq. The latest addition is a way of spotting alphabet hypermutations within the sequences, or that's also within the DRM-seq pipeline. And as I mentioned, the reference mapping looks at matches each read to the closest matching reference. That could be a clade, B, D, F, whatever. And if it doesn't find, and if it makes if the alignment is poor, then there is a step for filtering off very poor alignments, assuming that they're garbage. I mentioned that it can that you can use this for the whole genome. It handles DRM indels, and because the sequencing is quantitative, we think we give a good we do a good job at least providing the data with which we can use to understand the importance of minority variants. The other useful thing with looking at drug resistance at the read level first before you summarize is that you can get to grips with the importance of combinations of mutations that are observed within the same virus particle, but within limits of the read length or the insert size, which is between around about 250 to 500 nucleotides. A more detailed description of how DRM-seq work is shown in this slide. So the three inputs that you need to give it are the reads, which are the reads that are cleaned first of all by Filoscanner to remove contaminations and trimmed, etc., using Shiver. You then give it a codon-aware multiple alignment, and such curated alignments exist in the Los Alamos database. And so here I've given an example of a clade B, D, C, B, D, and F. And your HXB2 reference needs to be in there as well. And then if your reads will then pick out the closest matching reference, and then it will use that multiple alignment to work out what the coordinates of those bases are relative to the HXB2 reference. The third input to the pipeline is the flat files that are available from the Stanford algorithm that just give you a scoring system for each of the drugs with respect to each mutation. And the outputs are shown on the right, so you will end up with a kind of a summary of the level of resistance you observe to each drug and a list of mutations encountered within each read, and that information is then summarized, but you summarize it while filtering on mutations that don't reach a threshold that you might specify according to so you might say that you don't want to know about any mutations that are observed less than 5% of the time or 20% of the time. You can specify that, or you can specify your threshold according to the number of reads that you obtain. So overall, the impact. So this is just a slide to show the impact that drug resistance appears to be having within Popart at the moment on the odds of virological failure, depending on whether or not we observe only non-nucleoside reverse transcriptase inhibitor resistance, NRTI resistance, and some of the individual mutations up at the top. So the two more common NNRTI resistance mutations that we see here are the K103 mutation. So that's the K103 mutation on its own, and here is that's the K103 mutation on its own here, and the E138A mutation without the K103 mutation here. You can see that the K103 mutation, the odds fall within the region of around 4. The outline, there's a log scale on the odds, so it's around between 3 and 4 odds for K103. And we don't, when you observe the E138A mutation on its own, it doesn't seem to be associated with virological failure. Which is perhaps not surprising for what's known about E138A, given that it associates, given that it doesn't associate with resistance to the drugs that are commonly observed in Zambia. But it's interesting, so it's therefore interesting, I think, that we're seeing so much of it, and we need to do some work, I think, to work out why E138A is so prevalent, and why its prevalence seems to be increasing, and why, if it is increasing, and why it seems to associate with the resistance mutations if it's not having an effect. And I have some more information to show on that in a little bit. Looking at low-frequency drug resistance mutations, there have been many studies that have looked at whether or not they are important, whether or not they matter, and I'd say more studies that have been conducted tend to fall on the side of the fence, suggesting that they don't have an impact. But of course, it depends on how you define a low-frequency drug-resistant mutation. But there are a handful of studies that show that there may be an impact. And this is an idea that has been floated by a handful of studies, that actually we tend to define drug resistance mutations by their percentage prevalence, but actually what perhaps might be more important is the actual mutational load, the amount of the number of virus particles within the host that have those mutations. And if you think about a 1% mutation of a K103N in somebody with a viral load of 1,000, well, you're expecting to find 10 mutants per mil, but you'll find 1,000 mutants if that patient has a viral load of 100,000 copies per mil viral load at the same percentage prevalence. I've checked that maths; it's right. And so I mean, this is an idea that's been floated by a number of groups now, and some studies have looked at this in some more detail. I should thank first of all Corinne Metzner, who actually I filtered this the list of a comprehensive list of studies that have given that associate with treatment failure or not. And again, this is a study by Lee that quite a long time ago attempted to look at the number of copies, how the number of copies associates rather than percentage prevalence associated with the odds of treatment failure, or the hazard ratio of treatment failure. And you can see a trend. I'm not sure if it's significant, but again, others more recently have tried to define a threshold, not based on percent prevalence, but on the mutational load, or the percent prevalence times the viral load. But I think these studies are it's an interesting idea, and certainly one that I would a hypothesis I would share. But I would say that we've not really had the tools to look at this at sufficient scale. And what you want, of course, is a highly quantitative sequencing method where you can be confident of the mutational loads that you obtain. And so I'm hoping that the methods and the pipelines that we developed will allow us to address this in more detail. And it's just a slide here from the paper that Tanya and I and others have deposited on bioRxiv at the end of last year, that just shows just how quantitative the sequencing is. Here are the standards, the standard curve that I mentioned earlier that we include within each run. From this, we were able to construct a model that we then use to infer the viral load based on the number of reads that you obtain. In figure C down the bottom, you see how if we just take samples and obtain a clinical viral load shown on the y-axis, you can see it correlates strongly with the sequence-derived viral load that we obtain using this model. And from that, you get the distribution of viral loads that we observe within the healthcare facilities. And can I just ask, is my sound not working? Is people still there?
It's working. I can hear. Okay.
We're here.
You're all being very quiet. You make more noise. Okay, so the distribution of viral loads is shown on D. I think the other thing I'd like to just say yes, I think mutational load is important, but I also think that the potency of mutation is also important, and that's not just in terms of the individual mutations, but how those individuals interact with each other. And with the method that we developed for next generation sequencing, we're actually able to get a better understanding, I think, of the epistasis, the interaction between these mutations. And then I'm going to demonstrate that here, because we're sequencing the virus swarms within a single host, and we're obtaining sequences that look like this. So the resistance mutations are shown here. Now, if we obtained a traditional Sanger consensus sequence for the same individual, it would look more like that. And you'd see that, where you've got low frequency drug resistance mutations, you display that in the chromatograms on the top. This is how we're used to looking at sequence data. And just consider these two individuals for a moment, and just consider that actually these two individuals would produce exactly the same Sanger consensus sequence, because at each position they have exactly the same number of mutations at each site, okay, that give rise to the same chromatograms. But if you look at the green patient on the left, you can see that this virus particle here that has 5 mutations all linked together, I would argue is likely to be more resistant than any of the virus particles sampled in the red patient. So it's just a simple cartoon, really, to show why I think that looking at drug resistance within host and spending the time to actually look at the mutational load of each individual read is the right way to go. And I think that's important because you got a clue for kind of what we're thinking of doing here, which is kind of linking the information that we observe on the reads, the mutation information, to the phylogenetic information and the transmission information that Matthew and Chris's pipeline can produce. So you get a feel within the Popart data straight away that of how important transmitted versus acquired drug resistance is. So these are individuals that enrolled in a healthcare facility where they're asked, did you have you previously had antiretroviral therapy in the past? And a proportion of those individuals will say that they have, and they're shown, the men and the women are shown there, and a portion of those will say that they haven't. And I'm only looking at individuals that have answered the question here, and so the bars that are coloured red and pinky red are those viruses that we would call resistant. And you can see much higher levels of drug resistance, higher prevalence of drug resistance reported in those individuals that claim that they've had antiretroviral therapy in the past. And those individuals that deny that they've had antiretroviral therapy have lower levels. Now, of course, if all these individuals are telling the truth and these individuals have never had exposure to antiretroviral therapy themselves, then you could say that the level of resistance you observe in this group represent your transmitted drug resistance, and the difference between these groups represents the amount of drug resistance that you might expect to acquire. It's not as simple as that, of course, because a proportion of these, because we suspect that a proportion of individuals will deny that they've had antiretroviral therapy in the past, and we think that because of the high levels of viral suppression that we observe, suggesting that individuals, even when they're saying that they're not on antiretroviral therapy, might actually be taking suppressive treatment. So you can get a feel for it, but you can't know for sure. This is just one other analysis where we've actually looked at the ancestral state, where the state that we're defining here is NNRTI resistance, just to see if there is evidence that drug-resistant strains are emerging within the communities within Popart. So again, an ancestral state reconstruction where we're trying to determine what the likely state, resistant or not, and resistant is shown in red, not resistant is shown in blue, what the likely state of the ancestors of the sequences that we've sampled. And you do, see one or two patches within certain communities where there are clusters, appears to be clusters, perhaps another one there, of resistant virus. And I mean, this is at the consensus level. It'd be nice to do this at the more linking directly with the phylloscanner approach that Matthew and Chris have developed, where, of course, just to remind us, when we sample the swarms of viruses within two individuals, we are able to reconstruct the ancestry of all of the virus particles we sequence from individuals together, and say something about the likely origin, for instance here, of the blue virus, the ancestor of the blue virus, and how that relates to the sequences within the red sample from the red individual. And when you do this across the genome, you can start to build a picture of transmission, and in this case, this would suggest that the red patient infected the blue patient. When you do this for all individuals, you can draw networks like this. Well, I can't, but Matthew's very good at it. So I'll just very briefly switch to just to show you what we've got. So this is now linking DRM-seq pipeline to phylloscanner. So I can control the windows. So here, just to orientate you, you've got the tree of the sequences sampled within host. And I've annotated the sequence as either the transmitter or a recipient. And that's based on Matthew's analysis using phylloscanner. The number of times you observe a sequence is shown by the size of the node, and you can get that from the recount here. And the color gives you the mutations that we're observing within that sequence. And this heat map is the heat map, a similar heat map that I've shown before, which is just saying, well, what does that mean in terms of drug resistance to the drugs that are shown down the bottom? And so you can see here, for example, that the recipient has a V106M mutation, and whereas the transmitter actually has, in this window at least, didn't have any of these mutations. If we scan across the genome, as phylloscanner does, you can see that the transmitter had an E138A mutation, in fact, but then the recipient seems to develop, seems to have more, and so you get a feel for how that seems to have emerged. So I can just show you maybe one or two more, and this is the end of my talk, so apologies if I've gone over, but if we look at a different cluster now, so this is cluster 160, again 2 individuals. So if we start somewhere like here, so you can see the transmitter and the recipient sequences that are shown here, and most of the sequences we obtained from the transmitter were in this window, don't have the mutations that the recipient has. If we scan across, we can kind of get a feel for what the pattern of drug resistance was, and I don't know. You might get a feel for. It's difficult, of course, because you have to look at each window individually, and we're developing methods to kind of summarize the information you see across. But maybe you get the suspicion that it was a D68, D67E mutation that was inherited from the transmitter, because we also see that in the recipient, and then you end up with more mutations that seem to arise within the recipient, and a kind of spread of drug resistance. That maybe just one more. Let's try. I'll be honest, I'm fishing out interesting. I'm not just honest, but. So yeah, so here's a good one. You see that the 106M, the 106M mutation seems to have been inherited from the transmitter, but they also seem to have acquired all these, who subsequently seem to have acquired all these additional mutations on top of that. So again, giving you a kind of direct visualization of how drug resistance seems to have been transmitted and then built upon by and expanded within host. So that, I think, is kind of everything I wanted to show you. I appreciate it was a kind of I've probably gone over time. I've shown quite a lot of different stuff and not really summarized it very well, I suppose. But yeah, just to say that this is a cheap method. It's a whole pipeline though, and it's important to think of this as a method that includes the analytics. I think that we should give thought to the translation of methods that are now so fast and so cheap, and how we can best use them in low-income settings. And I'm interested to hear what people's thoughts are on that.
Thank you very much, David, for